Rays from infinity, 6th orbit, 5th orbit, 4th orbit, any of the orbit will come and will rays means what? Electrons will jump from any of these orbits. You can see, look here, this is infinity. This is marking 6th orbit. This is marking 5th orbit. This is marking 4th, 3rd, 2nd. All these rays will come and get accumulated, and all the electrons will jump at first orbit. This is known as the ground state, n is equal to 1. Then apart from this, if any electron jumps from any of the orbit and jumps to second orbit, we call those spectral groups of lines as Balmer series. Fine. Then if all the electrons, or from any electron from any of the wave number, any of the shell, that is infinity, 6th, 5th, 4th, lies and jumps to third, resides at third, does not move further, we call these series as Paschen series. Clear? If the rays move, not the rays, basically we can say electrons jump from infinity, 7th orbit, 100th orbit, 3rd, or any of the orbit, 6th orbit, and reach up to the 4th one, we call these series as bracket series. And finally, when the electrons jump from any of the orbits but land up to the 5th one, we call these as fund. So class, the first one lies in the UV rays, means whatever the electrons are ejected, no, their wavelength lies in the spectrum of ultraviolet radiation. Same in case of Balmer series. In case of Balmer series, all the electrons' wavelength will lie in the electromagnetic spectrum of visible range. And last three, bracket, fund, and Paschen, all these series have their radiations at infrared. Now class, till here, this is clear. This is what we had done in the last class. Now see, certain values I have marked here on the left-hand side. These are basically energies. In the last class, remember, we had written one formula of energy. E is equal to minus 13.6 Z square by N square. Yes or no? Did you all revise it or not? Check into your notes. You must have written it. E is equal to minus 13.6 Z square by N square electron volt. Is it written or not, class?
Written.
Written, no? So respond. What about other students? Otherwise, I have to call everyone's name. If only Atif is responding to everything. Fine, classes. Now see, for hydrogen atom, Z will be 1. Z is 1 for hydrogen. Remaining is N square. So N square value, if you keep, you will be getting these values. Let me show you. See here. E is minus 13.6 by N square electron volt. If I put 1, N as 1, I get minus 13.6 electron volt only. If I put N as 2, so minus 13.6 divided by 4, I get it as minus 3.4 electron volt. Same thing. If I write N is equal to 3, that is minus 13.6 divided by N square, that is 3 square, that is 9. I get minus 1.51 electron volt. If you take N is equal to 4, you get minus 0.85 electron volt. For 5th orbit, you get minus 0.54 electron volt. And for the 6th one, it is minus 0.38 electron volt. Now, from this class, what things are important? No. See, all these values I have written. And obviously, for infinity, you can understand N is equal to infinity. Means 1 by infinity is 0. So here energy will be 0 exactly at infinity. Now class, you have to remember the values at least till 5th or 6th orbit. At least try to remember these much values. Don't go further for 7th, 8th or 9th. That calculation you can perform. But these are very common in your exams. 3, 2, 1 and 4. At least till 4th one and 5th one. 5th one minimum. You should remember all these energies values, because that will ease your calculation. Your calculations will become faster. Clear? Like energy for 5th one, then first you will calculate this, solve this, apply mathematics, and then see whatever is the question. It is better if you remember this value, because many cases you will find E5 minus E3, E2 minus E1. So if you remember these values, that will become easier. Understood? Do one thing before we move on to the limitations of Bohr's model, no. Make this spectral line series. This is known as energy level diagram. Make the energy level diagram and the same thing, the energies values. Then we'll do the limitations of it. Any doubts you have in between, let me know, class. Class, did you receive the notes on WhatsApp? I had sent you some notes on modern physics. Did you all receive it? Did you check it? Modern physics notes I have sent. Okay, so Kulsum, Atif, Zain, Hazifa. Okay, fine. So see, class, everything is now written perfectly in those notes. Even some extra things are written, those things that are not part of your syllabus and which we have not discussed in the class, the dual nature of matter and dual nature of radiation and matter. In that, we do not have Davison's and Germer's experiment. All right, so that is also given in detail. Okay, so everything is given. So do refer those notes because many things I have not written in the class because modern physics is completely theory based. Like the limitations, I'll discuss it right now here. But for the complete statement, no, whatever is given in the class, prefer and refer to your notes. Now see, first limitation of Bohr's theory. First limitation of Bohr's theory that this is, see, continuously I was saying you Z is equal to 1 for hydrogen, Z is equal to 1 for hydrogen. So limitation is this only, that it is applicable for hydrogen and hydrogen-like atoms only. All right, hydrogen-like means single electron atoms. So what about the atoms that have more than a single electron? That do not fall in this category. So it's a limitation. Fine. Then second limitation says that, see, these spectral lines which we have studied. Look here. In the spectral series, there is not a single line. If you see, this is not a single line that is coming. This is entire group of closed lines. So it means even if I talk about Lyman series, every radiation will be having its own different frequency, right? So that becomes a limitation. These are not single lines. These are group of closed lines. So group of closed lines have slightly different frequencies. So it means Bohr model is not justifying every frequency. It is just referring to spectral series overall. So that's why this becomes the limitation of it. The second limitation is that in the spectrum of whatever is the hydrogen, spectral lines have different frequencies. Spectral lines have different frequencies. Fine. Now, third limitation. Third limitation is that it says that circular orbits exist. Circular orbits are present, which has centralized nucleus and electrons revolve around the circular orbit. Fine, that is fine. But see, elliptical orbits are also possible. In elliptical orbits, rotation exists. In case of elliptical orbits, like even the Earth's orbit, that is elliptical in shape. So all these elliptical orbits are also possible rather than the circular orbits. So it didn't justify anything for the elliptical orbit. Right. Circular orbits are possible, but what about the elliptical orbits? So that's why it became one of the limitations. Fourth point says that, see, in dual nature was what? One, dual means two. So one nature, that is in the dual nature, one nature says that electrons are particle objects. That describes the whole particle theory, that is photoelectric effect. And second phenomena that is present in the dual nature only. So that second phenomena describes what? That second phenomena is wave nature. So here in Bohr's theory, we started with the dual nature, that is de Broglie's wavelength and everything. But here it didn't consider anything regarding de Broglie's wavelength. So electrons exhibit wave properties. So orbits of electrons cannot be exactly defined in Bohr's theory. So that became the limitation. Wave properties. Because it was proven by de Broglie that yes, electrons have wave-like characters. Fifth limitation is that, see, fifth limitation, no, it consists of actually two terms, Zeeman effect and Stark effect. These are two phenomena that occur. Zeeman effect Zeeman effect basically says, see, the spectral lines we have been studying, but those were in vacuum, right? So what will happen if all these splitting of spectral lines occur in magnetic field? So the splitting of spectral lines in magnetic field is known as Zeeman effect. So Bohr's theory didn't explain that if these spectral lines are there in magnetic field, what will happen? So that became a limitation. One more phenomena that you have is Stark effect. So in Stark effect means the splitting of lines, spectral lines in electric field. So we didn't Bohr didn't mention anything about magnetic field and electric field. So if nothing is mentioned about magnetic field and electric field, it means it is a limitation of this theory. Something is missing. We do not know what will happen to magnetic field. Will they exhibit the same phenomena or not? Will the spectral lines will split or not? Right? Or spectral lines formation will occur or not? So that is Stark and Zeeman effect. So these were also not explained. So everything is given in the notes, but you can note down these points. Just note down these points quickly. Then we'll do one small topic is left, excitation and ionization potential. Now coming to excitation potential and ionization potential, these are two topics. See, excitation, just a second. Excitation energy and excitation potential is one topic, and then you have ionization energy and ionization potential. See, excitation energy means what? Excitation energy is basically the energy that is required by the electron to jump from ground state to any of the excited state. See, energy that is required by the electron to enter, just to jump from any of the from ground state to any of the excited state. It means this is the electron, this is the nucleus. Let's say this one is, let's take this one is n is equal to 1. This is n is equal to 1. So electron is jumping from this state to, let's say, some n is equal to 3. N is equal to 3 state. So energy difference will be what? Energy difference will be E3 minus E1. So as I've told you, please remember all these values. E3 was 1.51 minus. E1 was minus 13.6. So C, the difference is 12.09 electron volt. Let's say electron didn't jump to 3. Let's say electron only jumped to second orbit. So energy will be what? E2 minus E1. So E2 is minus 3.4 and E1 is minus 13.6 with a minus sign in between. This gives you 10.2 electron volt. That's why I was saying E1, E2, E3, E4, E5. Till E5, remember all the values. Learn it, because this way it will be used in the questions. So see here, do you notice? Here one thing is fixed. E1 is coming here. Here also E1 is coming. It means energy of the ground state is fixed. Ground state means n is equal to 1. This is fixed. And n is equal to n. This is not fixed. So this energy that is required to move an electron from this ground state to any of the excited states. First excited state, second excited state, third excited state, any of the excited state. What is meant by excited state? What is third excited state? Yes, what is third excited state?
Electron moves to the fourth level.
Fourth level, good. Ground state is 1. First excited state means n is equal to 2. Second excited state means n is equal to 3. Just one higher because ground state is covered. Right, like this excited states are covered. So any of the excited state means if you just forget the ground state, n is equal to 1. N is equal to 1 means this is the nucleus. The first orbit is known as ground state. This is known as ground state. So any other orbit that is present. So the amount of energy is known as excitation energy, and the amount of potential that is known as excitation potential. The accelerating potential that is required. See here, accelerating potential that is given to electron to excite the target atom by raising one of its electron from an inner to outer orbit. Same thing, see, the amount of energy to remove an electron from ground state to any of the states is known as excitation energy, and the potential that is required to excite the electron from ground state to any of the state is excitation potential. Fine. Now, what is meant by ionization energy then? Ionization energy means to completely remove an electron. Means throw the electron to infinity. Remove the electron entirely from the atom. Not even first, second, third. See, in the previous case in excitation energy, n is equal to 1 was fixed for the ground state. And rest of the states were not fixed. Right now, no state is fixed here. The state that is fixed is infinity. Even if it is at n is equal to 100, it is the electron is at n is equal to 1, and electron is at n is equal to 4, electron is at n is equal to 5, any of the states. Whatever is the energy to throw the electron, completely knock the electron out of the atom, that is make the electron reach infinity. That is known as ionization energy. And same thing, whatever is the potential required to remove an electron out of the atom, that is known as ionization potential. Ionization energy you do in detail in chemistry. So it is defined as the energy required to knock an electron completely out of the atom. Basically, let's say if I'm removing the electron from the first one, let's say from the first one I'm removing, first orbit. So ionization energy will be E infinity minus E1, that will be minus 13.6. That will give me plus 13.6 electron volt. Any value, if you take any one value, if you are taking ionization energy, let's say from second orbit, you are removing electron. That will be E infinity minus E2. And E2 is minus 3.4. So minus 3.4 will become 3.4 electron volt, like this. So here, which state is fixed? Here, E infinity is fixed. E infinity is fixed, and E infinity is 0. And same thing is with potential. Whatever potential is required to completely the sufficient energy to ionize the atom. And now the electron, once the electron is removed, so much of positive charge is contained within the atom because electrons have been removed from the atom. So we call that these are known as these atoms. We call these atoms as ionized atoms. Tell me, is it clear till here? Akifa, Afra, Fatima?
Yes, teacher.
Because then after this, we'll do numericals. That's why I'm asking. Huzaifa, Hiba, clear to you? Okay, then note it down. If anybody has any doubt, ask me. After this, we'll practice some numericals from this lesson. 2 to 3 numericals at least we should practice. So note these portions, then we'll do it. Done till here? All of you? Still writing or what?
Teacher, can you scroll up 1 minute?
Yes.
Teacher, here only. Okay, teacher, thank you.
Okay, then let's practice some numericals then from this lesson. So it says that the ground energy of hydrogen atom is minus 13.6, right? What is the kinetic energy of an electron in second excited state? What is the kinetic energy of electron in second excited state? Right. So, yes, Hamza, what do you mean by second excited state? Hamza, second excited state. Anyone else apart from Hamza? Hamza has answered. Yes, Zen. Second excited state. Shara is correct. Akifa is right. E1 means Zen, first orbit. Zen E1 means what according to you? First energy. Second excited state, Hamza. Second excited state. It is written here. Look here. Second excited state. First part. I'm asking you this. N is what? Few students have answered it correctly. Akifa has answered correctly and Sara has answered it correctly. No, Atif, wrong answer for the first part. Second orbit of hydrogen, no class. C, ground state means N is equal to 1. First excited state means N is equal to 2. So second excited state will be N is equal to 3. Whenever you have excited state, just enhance one more orbit. So for the first part, you will have N is equal to 3 because this is second excited state. So ground state N is equal to 1. First excited state N is equal to 2. Then second excited state N is equal to 3. Now clear to the rest of you. So kinetic energy, you can say, or the total energy, you can say. See, total energy, you all know. Total energy's formula we have done right now. Energy in the third orbit. That's why I was saying till fifth, at least remember. Like energy in the third is 1.51 minus 1.51 electron volt. And kinetic energy is negative of the total energy. So it will be minus 1.51. That will be plus 1.51 electron volt. This will be the answer. Second part says, what is the potential energy? Not minus 1.5, Atif. That is the total energy which you are mentioning. Question is asking kinetic energy. So it will be plus whatever answer you've written. What is the potential energy of an electron in the third excited state? Huzefa, third excited state. What should I consider N? or third excited state? Huzaifa Ahmed. Fatima, correct. Huzaifa. No answer from Huzaifa. Zain, correct. Hamza, correct. Hanifa, Hiba, Afra. Answers from you. Hanifa, right? Because this is the main thing. Formula putting you all can do. Good, Hiba. Afra, you also try. Afra. Rishan. Rishan hasn't answered anything yet. Shara, good. N is equal to 4 class. No, see, ground state 1. First excited state, N is equal to 2. Second excited state, N is equal to 3. So, third excited state, N is equal to 4. So, total energy, that is E4. This was E3. E4 is minus 0.85 electron volt. Now, potential energy is double of total energy. So potential energy will be 2 times E4. That will be 2 into minus 0.85. So this will be minus 1.7 electron volt. This is how you will solve the second part. Third part says, class, if the electron jumps from ground state, jumps to the ground state from third excited state. It means third excited state is fourth one, which we have just written. So from the fourth, it is jumping back to the ground state, that is E is equal to 1. We have to find out wavelength. So if you know what is the energy right over here, you can easily calculate the wavelength. No, class, you can easily calculate the wavelength if you are aware of it. So energy will be E4 minus E1. That will be the energy. And this E4 minus E1, let me write down this. This will be minus 0.85 and E1 is minus 13.6. So both are getting subtracted. This will become plus. So 12.75 electron volt. We have to convert it into joules because wavelength will be in meters. And for SI unit, we have to convert this also into the SI unit of energy. Now you know energy is hc by lambda. So wavelength will be simply lambda is equal to, from here lambda is equal to hc by energy difference that is coming. So lambda is hc 6.63 into 10 to the power minus 34. C, speed of light, 3 into 10 to the power 8 meter per second. Change in energy, that is this term, 12.75 electron volts. So we have to convert it into joules so that we get our final answers in meters. This will come out to be 970 angstrom, class. Please solve and check whether this is the answer. I remember it, so I have just written it. Otherwise, you calculate it. 970 angstrom, something like this, you will get the answer. Note down this question, note down the solution, then we'll practice other questions. C class, some questions you will be getting directly where written part will be mentioned, but in some questions not like this, you will get proper energy level diagram as well of hydrogen atom. Now from here questions will be asked to you. Like the first part says you have to find out the transition. See, these are certain transitions given. In this part, this electron is jumping from 4th orbit to 3rd orbit. Here it is jumping from 4th orbit to 2nd. Here from 4th to 1st. Here from 3rd to 2nd. In this one from 3rd to the 1st. This is electron is jumping from 2nd orbit to the ground state, that is 1st. So this is ground state. This is 1st excited state, 2nd excited state, 3rd excited state. Now we have to find out of all these transitions, 1, 2, 3, 4, 5, 6, which transition means energy difference will correspond to the wavelength of 496 nanometers. So let us find out how much is the energy difference, so then we can at least estimate it, right? So for the first part, let us find out what is the value of energy difference. E is equal to hc by lambda. So energy will be 6.63 into 10 to the power minus 34 into 3 into 10 to the power 8. Wavelength is 496 nanometers. So this becomes 496 into 10 to the power minus 9. And let us now convert this into electron volt by ourselves only. 10 to the power minus 19. Why? Because see here, we know the answers, no, E4, E1, E2 in terms of electron volt only. Like E1 is minus 13.6 electron volt. So if we have this also in electron volt, it will become easier. We don't need to calculate then. I have told you, no, at least remember till E4, E5. If you remember till E5, E6, all your questions will become very easy in your exam. Try to remember it. Just wrote it, the values. Read it 4 to 5 times. You'll be able to learn it. This will be around 2.5 electron. Now see, E1 is minus 13.6. E2 is minus 3.4 electron volt. E3 is minus 1.51 electron volt. E4 is minus 0.85 electron volt. Right. Now what we'll do, see, 4 values are given. You have to do hit and trial method and you have to analyze. Minus 13.6 minus 3.4. That is minus 13.6 plus 3.4. That is around 10.2, like this. So we need a bigger gap. Let's see second and fourth. If you know like this, you will figure it out. And then you'll find E4 minus E2, that is minus 0.85 minus 3.4 electron volt. This will be, see, this will become plus. So this will be around 2.55 electron volt something. So it means the transition from 4th to 2nd. Look here in the diagram. Identify which is the 4th through 2nd one. This is 1, this is 2, this is 3, this is 4, this is 5, this is 6. Tell me which one is 4th to 2nd. Tell me the number.
2.
2. Correct. So it means, yes, Sarah, correct. This one corresponds to the transition. Like this, you have to identify questions. One method is that you can keep on checking for every value, find out what is the wavelength. Like E4 minus E3, get the value, find out wavelength. Then E4 minus E2, find the wavelength, see which wavelength is matching, 496. But if you find out wavelength first, then finding out energy difference is better. So I'll suggest first using wavelength, find out the energy difference, because plus minus is easier than putting the value for and finding out wavelength, putting HC by lambda every time. Fine. Now, second part is also there in this question. The second part says that which transition corresponds to the emission of radiation of maximum wavelength. Now, see, if you look here, E is equal to HC by lambda, you know. So energy is inversely proportional to wavelength. And the question is asking you maximum wavelength. For maximum wavelength, energy has to be minimum. If energy is minimum, when can energy be minimum? Energy can only be minimum when the difference in the energy is very less. Rest of the energy's difference is high. So very less energy difference, you will be able to find it from fourth to third. Because in third to fourth, in this one, in this energy, even E3 minus E2 is there. That will be having some value 12 point something. But when you subtract this, 4 minus 3, that will give you even a lesser value, 4 to third one. So it means the lesser energy, we'll prefer this. That's why I'm saying continuously, learn till E5, like this. E4 minus E3 you can calculate, E4 minus E2, all these values you can calculate. And until which value will the question will be maximum? Till E6 only. More than E6, the question paper will not have the shells, and it is not possible to draw every shell. And in most of the questions also, these values are given. And if these values are not given in some questions of previous years of CBSE papers, values of energies are directly given. So that also makes your work easy. These values are given, that is much better. But if the values are not given, they'll give you the values of these shells. So till E6, if you remember, you can get all the values. Understood? So for this is the answer for the second part actually. So energy is minimum in fourth to third transition. You can even check n is equal to 4, all the values that we have written. Note down this question, class. Any doubts you have in any part, let me know. One last question we'll do. See class, that's the last question. So this is that which level of doubly ionized helium, lithium, double ionized lithium, Li2 plus. This has the same energy as the ground state energy of hydrogen atom. Which level of lithium means N? And N of hydrogen is 1. Ground state means 1. So when it says ground state of hydrogen, this means N is equal to 1 for hydrogen. And N for lithium is unknown. The formula of energy is minus 13.6 Z square by N square electron volt. So let us write it for lithium. Minus 13.6. Lithium, what is the value of Z class for lithium? Periodic table, I hope you all must be knowing. What is the number of lithium in the periodic table? Hydrogen, helium, then Z's value for lithium. 3. Only Sarah remembers the periodic table. Hydrogen, helium, lithium you have. Then only no, you have the other elements starting. So this is 3. That means 3 square and N is unknown. This is because Z is equal to 3. That's why we have written this. And energy for hydrogen, minus 13.6. Z for hydrogen is 1. N is also given 1. So only this much by 1 square. And both these energies are same. It is written in the question, has same energy. So equate these 13.6 into 9 by N square is equal to minus 13.6. 13.6 minus 13.6 cancels. N square is 9. N is equal to 3. So third level of lithium coincides with the ground level energy of hydrogen. Clear? Akifa, Afra, Atif, clear to you?
Yes, ma'am.
Akifa, you present in the class? Clear to you, Akifa? Hamza, okay. Hamza. Okay, note down this part then. See, class, we are almost done with the lesson. Some things are written in the notes that you can refer to your notes, where I'm just telling you what all things are apart from the Bohr's atom, Bohr's postulates and Bohr's model of an atom we have completed. Now, apart from this, you have Thomson's model of an atom as well. Fine. So J.J. Thomson gave you must have heard of the plum pudding model, where he said that the way the electrons, or you can even say seeds in a watermelon or plums in a pudding, plum pudding model or watermelon model he gave. So according to him, all the positive charge is spread the way pudding is there, and the way raisins and the seed or the plums are there in a pudding, the electrons are kept on it. So that was the model that was given by him. But obviously, we know this is not the case, where electrons are just scattered and then within a specific positively charged matter. So that's why, firstly, spectral lines were not denoted by it. And then the explanation for the scattering angles that was given by Rutherford, it wasn't true. Now, what was the scattering angle experiment? See, basically, this is known as Rutherford's model, but in your NCERT also this is mentioned that this was given by Giger and Martin first. So this is their experiment actually, from which conclusion Giger and Martin, all right, Giger and Martin. So from which conclusions Rutherford drew. So he drawn the other conclusions from the same experiment that was given by Giger and Martin. So basically, they had taken a very narrow opening which led to a lead block, and inside the lead block there were radioactive sources of certain alpha particles. Radioactivity is now deleted in your syllabus, otherwise you would have studied in detail about radioactivity. And a thin chamber was there, then some devices were there. Basically what happened, alpha particles were scattered through a gold foil, very, very thin gold foil sheet. So first observation that he drew from this was that most of the alpha particles pass straight through the gold foil. When the alpha particles were hit on the gold foil, most of it, maximum, could pass straight. So conclusion, what can be drawn from this? It was concluded that if most of the spaces are present from which alpha particles are moving straight away, it means most of the spaces in an atom is empty. Right, most of the alpha particles pass straight through the foil, so most of the space within atoms must be empty. This was the first conclusion. Second conclusion was that very few alpha particles, very few means like out of 80,000 or 8,000, only one in 8,000 could get deflected through 90 degree. So if it is getting deflected by 90 degree, deflected by 90 degree, it means there is something present, some concrete matter is present, because of which it is getting hit and it is getting deflected in its path and not able to move on its original path. So that small concentrated part mass of an atom within the centralized part, you can say centralized concentrated part in very small region of atom is known as, now we call it the nucleus of atom. So it means there is nucleus. See, in J.J. Thomson's pudding model, there was no presence of nucleus. Positive charge with electrons between it. So to explain the large scattering of alpha particles, Rutherford only suggested that all the positive charge and the mass of an atom, this is concentrated in a very small region, which we call the nucleus of the atom. So secondly, first point was regarding the space, second point was regarding nucleus. Last point was mentioned was that very few got rebounded. It means they rebounded or deflected nearly by the angle of 180 degree, almost 180 degrees. Fine. So what conclusion he could draw from this? So conclusion he could draw was, if it is getting deflected by 180 degree, it means it is returning back to its position. So electron is negative. If electron is negative, it means nucleus is positive. This centralized part, that is nucleus, this is positive and electron is negative. That's why only though they are repulsive for each other. So the nucleus is surrounded by a cloud of electrons. he could conclude this, whose total negative charge is equal to the total positive charge on the nucleus, and that makes an atom electrically neutral. Remember when we had started with electrostatics and we were discussing the atoms, that time I had told you we'll see this part in detail in atoms. So yes, we had seen how the arrangement is within an atom, how the electrons are arranged within an atom. All the spectral lines also we have seen. So nucleus is there and so many orbits are there. Electron is not just scattered. And how an atom can be electrically neutral, that also you can say whatever amount of positive charge is present within the nucleus is equal to amount of negative charge present in the nucleus. Now, two things are there. All these things, now whatever I have spoken right now, you will be able to find it clearly written in the notes with well diagram, all the diagram of Rutherford, the graph, everything is there. Just have a read from it. Now, there is one topic that is known as the distance of closest approach. So in distance of closest approach, no, basically, let me tell you. See, this is the nucleus. Fine, this is the nucleus. So here what will happen when the alpha particle is coming, no, at this particular time, a moment, at this particular distance, the alpha particle is coming and it is getting deflected. It is getting deflected. So there is a certain region which you can see at this is a certain space that is created. So this separation, this is known as distance of closest approach. Because of the repulsion, it gets reflected till this distance only. This is known as distance of closest approach. Fine, distance of closest approach. So it also has a formula which you can remember. R naught we usually refer it. So this is 2kZe square. K, you know, I hope you know K, 1 over 4 pi epsilon naught. That is K. So 2kZe square by the kinetic energy of the alpha particle. Here, let me tell you that this K is 1 over 4 pi epsilon naught. This is the value of distance of closest approach. And one more thing that you can remember is, see, just assume that this is the nucleus. This is the nucleus. This I had told you, that the alpha particles were coming and they were getting deflected, let's say by some angle theta. So this separation, this perpendicular distance that is arising between the velocity of the alpha particle and the center of nucleus, this is known as impact parameter. This is known as impact parameter. So this is known as impact parameter. Now see, this also has a formula. Let me tell you, this is 1 over 4 pi epsilon naught K Ze square cot theta by 2, this theta by 2 divided by K. Fine. K basically, let me write it kinetic energy, otherwise it will be confusing with the constant. This is the formula for the impact parameter. All right. Note down these 2 points as well. This completes with atoms. I'll just introduce nuclei also because we have some time. Let us start with nuclei also. Nuclei is a very small lesson though. See class, in nuclear lesson, no, firstly you have the very basic thing. Class, this is now a very easy lesson. The difficult part was radioactivity, which has been deleted in your syllabus. So please revise it. Do not lose marks in this lesson. Atoms, nuclei, dual nature of radiation and matter, semiconductors. These have weightage also in your lesson, as well as these are direct, easy lessons from which portions have also been deleted. So please try to at least score in this lesson. Book 2 is a scoring book as compared to book 1. Now see, few terms you have to understand. So nucleons basically means protons plus neutrons. We call this collectively as nucleons. Atomic mass you have and mass number. Atomic mass nahi, atomic number this is fit. Atomic number. See, atomic number is basically the number of protons in a nucleus. Number of protons. And mass number means number of nucleons. Nucleons, not neutrons. Nucleons. That is number of protons and neutrons. Now see, number of protons, we represent this atomic number. Atomic number is represented by Z and mass number is denoted by A. So number of protons will be Z, atomic number. Number of electrons will also be Z, that is atomic number. Number of nucleons will be number of protons plus number of neutrons, that is A. And number of neutrons will be what? See, neutrons plus proton is A. So neutrons will be A minus number of protons, that is Z. So number of neutrons is A minus Z. Now, how do we represent an atom? This you have studied and are using this only in chemistry. This is the way you represent whatever is the chemical symbol. Like for chlorine, you write Cl. For calcium, you write Ca. For helium, you write He. And then you write the mass number on the top of it. And in the subscript, you write the atomic number. Like chlorine, 35 is also there. One isotope is 37. So 37, 17. Calcium, 40, 20. Like this you write. Understood? Helium. So this is the way you write this. Helium, this will be 3, 2 here. Like this, you keep on writing this. Understood? So this is just simple representation of it. Now, some terms are there: isotopes, isobars, isotones, isomers. These are part of chemistry only. You all study this in chemistry in detail, but let us also see this in physics. See, isotopes means Z will be same. Z will be same. Means atomic number will be same, but you will be having different mass number. Atomic number will remain the same, but mass number will be different. Just a second. Same, you will have here Z, that is atomic number, but different mass numbers. Like hydrogen. Hydrogen has 3 isotopes: protium, deuterium, and tritium. All of these are hydrogens. Same Z means below. This is same, but this is different. 1, 2, 3. These are the isotopes: protium, deuterium, and tritium. This is how you write. In case of isobars, isobars have same atomic number, same mass number, but different atomic number. Like if I give you the example of chlorine and sulfur. So in this case, chlorine is 37. This is 17. Sulfur is also 37 and this is 16 because below it is different. Or you can take the example of calcium and argon. Calcium is what? Calcium is 40. This is 20. Argons also, if you consider the mass number of argon, that is different. Atomic number is different. That is 18. So here 37, 37 is same. Here 40, 40 same. But below you have atomic number different. Only the mass number is same. Then you have isotones. Isotones means A minus Z is same. Number of neutrons remain the same. For example, if I talk about, let's say, let me give an example. Let's say chlorine and potassium we take. Chlorine and potassium. Chlorine, that to 37 mass number chlorine. So 17 is atomic number. Potassium is 39 and 19. See, take A minus Z here. This is A, this is Z. Here you will see number of neutrons, A minus Z, 37 minus 17, giving you 20. Here also take it. This is 39 minus 19. This is giving you 20. Both are same or not? So chlorine and potassium, these become isotones. And isomers, you all know they should have the same atomic number, same mass number, but different energy states should exist in this. All right. Quickly note down this class. Okay, class, there are certain values of masses that you have to remember in terms of atomic mass unit. Atomic mass unit basically 1 by 12th of the mass of carbon atom. So for electron, it becomes 0.00055 AMU. Then for protons, this becomes 1.0073 AMU. See class, these values you have to remember because in your syllabus, binding energy and mass defect is added, and there are high chances that questions from mass defect and binding energy can come this time. All right. So as to prepare for the same, prepare these values, also learn these values. Just practice it, you will be able to remember it. Mass of neutron is 1.0086 and mass of hydrogen atom is complete mass of proton plus mass of neutron. That makes it 1.0078 AMU. These values you have to learn it directly. Now, regarding the nuclear size, this is also a very small topic. Nuclear size basically says that volume of nucleus, this is directly proportional to the radius of the atom. Radius of atom. Not radius of atom, sorry, mass number. This is directly proportional to its mass number. So volume is 4 by 3 pi r cube, which is directly proportional to A. So directly you can say r cube is proportional to A. It means r is equal to, here a constant term will come to remove the, or you can say r is proportional to A to the power 1 by 3. Now a constant term comes, that is r naught A to the power 1 by 3. This r naught value you have to remember, this is 1.2 into 10 to the power minus 15 meters, or we also write it as 1.2 Fermi meter also. So questions are based on this also. Questions we'll do in the next class only. At least if you have the theory part, we can write this. And then coming to nuclear density, nuclear density is mass of nucleus by volume of nucleus. This is how we write density, mass by volume. So mass of nucleus by volume of nucleus. Let's assume m, small m is the average value of mass of a nucleon. So how will we write density? Mass density, nuclear density. Nuclear density will be written as, see, mass of nucleus will be mass, average mass of a single nucleon multiplied by mass number, that is A. And volume we write it as 4 by 3 pi r cube. R cube will be r naught cube A. Just now we have seen the formula of r cube. So if you write this becomes 3m by 4 pi r naught cube. Look here, A got cancelled. There is no A in your answer. This shows you what? This result is very important. This shows you that nuclear density is independent of mass number. It means if you talk about calcium, if you talk about strontium, if you talk about germanium, if you talk about beryllium, every atom, every element will be having, see, put the values 1.3 into 1.67 into 10 to the power minus 27, 4 pi, 4 into 3.14, and r naught cube, that is 1.2 into 10 to the power minus 15 whole cube. When you solve this, you get it as 2.3 into 10 to the power 17 kg per meter. This is the value for every atom that is possible. So we will see numericals based on this in the next class. For the time being, quickly note down all these points. In the next class, we'll see the questions on it. Please revise nuclei and come because we have to practice numericals. We'll do numericals. A small topic is binding energy that we'll do. That will complete off nuclei. And then we'll start with semiconductors in the next class. Quickly note it down. Those who will complete it till here, you all can leave. Already, I think just 1 minute is left. All right, you all can leave. In the next class, we'll complete this and start with semiconductors. Okay, thank you so much, class.
Thank you, teacher.
Thank you.